So today we're going to have Alex Wang talking to us. He's going to be telling us about exactness and SDP relaxations of QCQPs. And this is speaking skills talk, so should be extra good. All right, Alex, take it away.
Cool. Yeah, so thanks for the introduction and thanks for having me here today. I'd like to tell you guys about some recent work on SDP relaxations of QCQPs. I know that these acronyms may be unfamiliar to a few of you here today, so I will do my best to introduce everything slowly. Yeah, hopefully by the end of the talk, we will all be experts on QCQPs, whatever they are. All right. So let's get started. So I'm just going to first begin by introducing QCQPs and SDPs. So before I tell you formally what an SDP is, maybe I'll tell you first why we might care about them. So QCQP, this stands for Quadratically Constrained Quadratic Program. It's a family of highly expressive optimization problems. Okay, so you can think of it as some generalization of linear programming. But it's so expressive, in fact, that it captures many interesting and hard problems that we care about from a number of fields. So for example, in computer science, we can use QCQPs to capture problems such as max cut or max click. In operations research, we can use it for problems such as facility location or production planning. And even in engineering, problems such as the pooling problem, this is a problem from chemical engineering, or the truss design problem, a problem from mechanical engineering. These can all be captured as QCQPs. More generally, any binary program, that is to say a linear program with binary constraints, binary variable constraints, or any polynomial program can be captured as a QCQP with only a polynomial blow up in the size of the problem. So I guess, the first thing to note is that simply because it's going to be able to capture problems such as max cut and max click, this family of optimization problems, the QCQPs, are going to be hard to solve in general. Okay.
Question. When you say binary programming, do you mean integer linear programs with 0-1 constraints? Because you said linear program. Okay.
Yeah. So I guess right now I guess what I'm thinking of is just 0-1 constraints instead of like integer constraints.
Okay, got it.
Cool. Yeah. So these are going to be difficult problems to solve in general, but we're going to soldier on anyways and try to do what we can here. So before I tell you about how we're going to attempt to solve these problems, let me actually formally introduce the notation that I'll use. And I'm going to do this via analogy with linear programs, LPs. Okay, so this is just a quick review. Right, so in linear programs, we're given some m+1 many functions. Right, this is L0, L1 through Lm. These are linear functions mapping Rn to R. And we might express this fact as in this form here. That is to say, we're going to assume that L sub I, each linear function, can be written as the sum of a linear form determined by B sub I and some constant C sub I. Okay, and in this problem, we're asked to minimize the value of L0, subject to the constraint that L1 through Lm are each non-positive. Okay, so here L0 is the objective function and L1 through Lm are the constraints. Pictorially, that might look like this picture here. Right, we're going to pick some x from this gray shaded area. This gray shaded area is the domain, which is defined by L1 through Lm. And we're going to have to pay, I guess, the value of this orange function above it. This is the graph of L0 or L0. And one of the main things to note here is that linear programming is a convex problem, and this is going to play a large role in why we can solve these things efficiently. Okay, so now I'm going to tell you about quadratically constrained quadratic programs. Okay, and syntactically they're not going to look too different. The main difference is that I'm going to replace these linear functions with quadratic functions. Right, that is to say, I'm going to replace these. You can think of these as polynomials of degree 1 with polynomials of degree 2. Okay, so I'm going to have these functions q0, q1 through qm. They're going to be quadratic now, which is to say we still have the original linear and scalar terms and constant terms, but now we have this new third term. This x transpose a sub ix is going to capture all of the degree 2 terms in our quadratic functions. Okay, And the optimization problem hasn't changed too much. Right now we're just minimizing Q naught, subject to the constraint that Q1 to QM are non-positive. And pictorially, that might look something like this. Okay, so again, here I've drawn an example in 2 dimensions. Right, this feasible domain is this gray area down here. It's cut up by 3 quadratics. Right, so the first quadratic might say that the x variable must lie outside this circle. The second constraint might say that x must lie outside this oval. And the third constraint might say that x must lie in between these 2 curves. Okay, and the first thing to note here, I guess, is that these problems, I guess, visually look much more complicated. And in particular, these problems can be non-convex. Okay, so before I tell you how we're going to solve these things, let me tell you about one more object, right? So for those of you who know what this is, I'm going to be telling you about the epigraph of the QCQP. Right, so I'm going to just take the same optimization problem from the previous slide. This is the QCQP. Okay, and I'm going to introduce this new variable lowercase t. Okay, and I'm going to do this so that I can move the objective function into the constraint set. Right, so I'm going to move from this original optimization problem to this new problem where I'm minimizing t subject to the constraint that x is still feasible in the original problem, and t is now simply larger than q0. Okay, and the pairs x and t that satisfy this are informally just all of the pairs x and t that lie above the original orange graph. Okay, and I'll collect all of those pairs x and t, and I'll call that set script E, right? This is the epigraph set. And pictorially, that will look like this blue set in the middle here. Cool. And the final thing I'll note is that now that this objective function is linear, right? I'm optimizing some linear function over some set. I can actually take the convex hull of this epigraph without changing the value of the objective function. Okay, intuitively, I guess the lowest down you can go in the z direction of the blue set is going to be equal to the furthest down in the z direction that you can go in this pink set. Right, this, I guess, recall that the convex hull is the smallest convex set that encloses right, your given set. Okay, and I'll denote this convex hull, pictorially by this pink region here. I do want to say, I guess, today, right, I guess in this chain of equalities, we're saying that the objective value is going to be equal throughout, but it may not be the case that, if you give me some optimizer in this third program, that it's going to be an actual optimizer in the original program. Okay, but we're going to not worry about these issues today, and I will only talk about the objective value. Okay, so I guess on this slide, there are 2 quantities that I'm going to care about that I'm thinking of as the hard to compute quantities. The first is opt, right? This is the optimum value of the QCQP. Right? This is, in general, we will not be able to compute this quantity exactly. The second thing on this slide that it is going to be difficult to compute in some sense is the convex hull of the epigraph. Right? So what I mean by this is that it's going to be difficult in general to give concise descriptions of this convex hull. Why? Because if imagining that you could give me a concise description of this convex hull, I could simply put that description here, right, and hope to solve this problem using convex optimization techniques. Okay, so I guess what I mean by concise description is something that formally you should be able to separate over, but I'll brush aside those issues for now. And I'm just going to think of these 2 things as the difficult to compute quantities. Okay. Soon I'm going to tell you about this relaxation, which for those of you who know where I'm going, this is the SDP relaxation. And this is going to give me 2 separate quantities, 2 easy to compute quantities. Okay. And those will be comparable to opt and the convex hull, respectively. And then I'm going to ask the question of when those 2 comparisons are good. Okay, so this was just a very high-level overview of for those of you who I guess know where I'm going with this. But let me, I guess, before I tell you formally what the SDP relaxation is, maybe I'm going to tell you first a high-level idea of why we might care about convex relaxations in general, so that when I eventually tell you about the SDP relaxation, it fits within the framework better. Okay, so I'm going to move on to convex relaxations now. I'm just going to take a slight detour. I said like these QCQPs are going to be hard to solve in general, and one of the main difficulties here is that QCQPs can be non-convex, right? So pictorially, in my mind, I have this cartoon on the left here for a QCQP, right? So this QCQP can be highly non-convex, right? And what that means is that if we try to throw some of our favorite convex optimization algorithms at it, these algorithms can get stuck at local optima that are not also global optima, right? And in which case, we would be unable to solve these QCQPs exactly. The idea of a convex relaxation is that, in order to solve this QCQP, or to hopefully approximate this QCQP, what I can do is algorithmically, I can take my QCQP, this non-convex problem, and construct a new convex optimization problem, which I will refer to as the convex relaxation. Okay, so this convex relaxation is on the right here. It's just going to be some convex optimization problem which lies below the original non-convex problem. Okay, so that's this picture here. I have, I guess, suggestively labeled this convex relaxation as the SDP, and I'll get to that in just a second. Okay, and I guess the idea is that we're going to just, because now the hopefully this convex relaxation is easy to solve, so then we're just going to solve this convex relaxation and return the objective value that we find in this convex relaxation as maybe a surrogate for what we think the actual objective, the actual optimum value in the QCQP is going to be. Okay, so I guess there's a major piece of this puzzle or of the story that is currently missing that I get to tell you about, is that when we do this, we want to be able to say or be able to claim that this relaxation is going to do well. Right? We want to be able to claim that the objective value that we find from the SDP is going to be similar to the objective value that we find in the QCQP. Okay, so that gets me to properties that you might want of a convex relaxation. Okay, so I'm just going to start by just drawing again the QCQP cartoon on the left here. The first property that I'm going to claim that I'll talk about today is objective value exactness. Okay. So this is a property of a convex relaxation, and this property simply says that the minimum value or the optimum value of the convex relaxation, the one that I'm calling SDP, is going to match up exactly with the minimum value of the QCQP. Okay, this is nice because when this happens, solving this SDP relaxation and getting outputting its optimum value is going to find the optimum value of the QCQP. Which was a priori hard to compute. The second type of exactness that you might care about is convex Hall exactness. Right? This says that if you take the epigraph of this convex relaxation, the SDP, that is to say, if you take the area above this convex relaxation, I want it to coincide exactly with the convex hull of the epigraph of the QCQP. Okay, and in some sense, when this happens, right, this convex relaxation, in some sense, is the best possible convex relaxation you can get for the original non-convex problem. Cool. So, the main question that we're going to deal with today is we're going to try to understand when is it true that these two types of exactness hold. That is to say, when is it true that objective value exactness holds, and when is it true that convex Hall exactness holds. All right. So now, maybe I should pause for a second just to see if there are any questions before I jump into telling you about the SDP more formally.
So Alex, you don't really care about whether the objective value exactness is achieved at a point which is in common with the two?
Right. Yeah. So I guess one question you could ask is, in the case that objective value exactness holds, right, I would also, it'd be nice if solving the SDP would actually give you a solution, right, that actually coincides with the QCQP. I guess this can fail, right? For example, if you had some non-convex problem that has, two, like imagine, I guess, if this local optima were actually had the same value as the second one. And so in the SDP, right, or I guess the QCQP would have two local optima that are both global optima. And in the SDP relaxation, the line connecting these two local optima would, would have the correct global optimum value. But any point in between might not actually get the correct QCQP value. I'm not going to worry about those issues for today. Yeah, but I mean, they're definitely interesting. That's definitely an interesting question to ask, and something we deal with in our paper. Okay. Okay, so I'm going to move on now, and I'm going to tell you more formally what the SDP relaxation is. So I'm just going to copy, I know this is a lot of symbols on this page. This is nothing but the original QCQP, the non-convex problem. Right, this is just a minimum of Q naught subject to the QI constraints. And I've, and I've just rewritten, I've expanded each of these quadratics into their definitions. Okay, so the first thing I'm going to do here is I'm going to introduce a new variable, capital Y, which I will constrain to be equal to XX transpose. Okay, and now with this matrix variable, I can rewrite the original quadratic forms X transpose A sub IX with the corresponding inner products between the Y matrix and the A sub I matrices. Okay, and at this point, this problem is still non-convex because of this constraint here, this highlighted constraint. And so what I'm going to do to get a convex relaxation is I'm just going to simply replace this, this non-convex constraint with this following convex constraint. This convex constraint just says that the Y matrix, Y minus XX transpose, needs to be positive semi-definite. Okay, I guess for those of you who might not know what this means, you can, for now, I guess maybe just think of this as some fancy greater than or equal to sign. Okay, and by doing this, we in general will get something smaller. Okay, but this program on this final line here is actually, I claim, is a semi-definite program in SDP, and is actually efficiently solvable in general. Okay, so, it's efficiently solvable up to numerical issues that I'm not going to worry about today. Okay, and I'll call its optimum value opt sub SDP. All right, so, I guess, the first part of this story was opt, right? The original objective value can be lower bounded by this new easily computable quantity opt sub SDP. And the first question, right, objective value exactness is going to ask when these two quantities actually hold at equality, right? When this inequality holds at equality. Okay, and if you will recall, I guess, the second question that we were interested in was whether or not the epigraph of this set lined up with the convex hull of the epigraph of the original QCQP. So let me just quickly, I guess, derive for you the SDP epigraph. Right, we're just going to copy the SDP from the previous slide. And we're going to, again, introduce this new variable t so that we can move the objective function into the constraint set. And now this, I guess, the feasible domain in this program here, I will call that the SDP epigraph. Okay, and I will denote that by this symbol script E sub SDP. Okay, and I guess pictorially, I will always denote this with a green convex set like this picture here. Okay, so let me, I know this is a lot of new information for some of you, so let me just quickly recap what I've said so far. So in general, QCQPs are going to be hard to solve. But because they're so expressive and they capture so many interesting problems, we would still like to be able to do something with them from time to time. So what we're going to do today is we're just going to solve the SDP relaxation instead. And we're going to ask, when is it true that A, or that, first, this convex hull exactness holds? That is to say, when is it true that the pink convex hull of this blue epigraph set, when does that coincide exactly with the SDP epigraph, this green set on the right here? And second, another interesting question is to ask, what are sufficient conditions that ensure objective value exactness? And as to say, when is it true that opt is equal to opt sub SDP? Okay, so I guess the first thing to note is that convex hull exactness will immediately imply objective value exactness, right? This holds simply because I guess the QCQP is going to find the minimum value in this blue set, right? The minimum vertical value in this blue set. And the SDP is going to find the minimum vertical value of this green set. And so if these two sets, if they coincide, then objective value exactness is going to hold immediately. But I do want to say, though, that convex Hull exactness is interesting in its own right, and not just as a sufficient condition for this second exactness result. And what I mean by this is that convex Hull exactness, right, being able to convexify non-convex structures, this is something that's done a lot in trying to heuristically solve difficult problems, right? So I guess, in a lot of, under the hood in a lot of binary programs or integer programming solvers, under the hood in a lot of these global solvers is convexification techniques that look something like this. Okay, so I won't get into this too much, but hopefully you'll take my word that convex Hull exactness is also an interesting question in its own right. Okay, so now let me give you an outline, and then let me just give you an outline first of the remainder of today. So the main result that I want to get to today is this result that Fatma Kalinskar-Zen and I proved at the late last year. So this result is going to say that if our quadratic forms, that is to say the A sub I matrices, if they interact nicely with each other, and if each quadratic form, the A sub I matrices, each have large amounts of symmetry, then we will have the convex Hull exactness. Okay, and in order to tell you, I guess, to make this statement more formal, I will have to tell you, what these two phrases in quotes mean. And to do that, I'll need to tell you first about the set of convex Lagrange multipliers. Okay, this is just some object in the dual space that I will define for you. And somehow it's the set's geometry is going to capture how qualitatively these quadratic forms are interacting with each other. Okay, and so for this result that I'm going to get to, I'm going to make some assumptions on the geometry of this set. The second thing I'll need to tell you about is this parameter that we introduce. We call it the quadratic eigenvalue multiplicity. Okay, this is a parameter. You can define this parameter one for each QCQP, and this parameter is going to capture, in some sense, the amount of symmetry inherent in your problem. Okay, and I guess in this second phrase that is currently in quotations is going to make some assumptions on the value of this parameter. Cool, and then time permitting, I'm going to get to an example application in the area of, for the problem of robust least squares. And I'm going to conclude with some additional work that I've been doing in this area, as well as some future directions. Cool. Are there any questions in the room right now that I might be able to answer? I guess now is a good time to clarify any questions before we jump into the technical material. Okay, maybe I'll just get started on this then. So, okay, so now I'm going to tell you about the set of convex Lagrange multipliers. And this is the usual story. I'm going to start with the usual story of Lagrange aggregation. Okay, so right in Lagrange aggregation, we're going to have this parameter. We're going to have this variable gamma. Right, gamma is you should think of this as your dual variable. Right, it's going to be some vector, I guess, that lives in Rm. Right, Rm, recall M here is the number of constraints. Right, this gamma is assigning some non-negative value for each of your constraints in your problem. Okay, and I'm going to define Q sub gamma as the aggregation of Q naught with the QIs, where each QI is going to be weighted by gamma sub I. Okay, I guess the two things to notice here are that for each fixed gamma, this expression is going to be quadratic in X, right? And that follows simply because, I guess, summing up polynomials of degree 2, you're going to get another polynomial of degree 2. The other thing to note is that when X is fixed, right, you might imagine fixing X and varying gamma instead. And when you do that, this expression is going to be linear in gamma. Okay, and this is going to come up to be useful again in just a few slides. All right, so what is the story of Lagrange aggregation, and what does it say? It says that, if you give me any gamma, for example, this in the picture on the right here, if you give me any gamma, which is not negative, and you give me any pair x and t from the original QCQP epigraph, then you're necessarily going to have that q sub gamma of x is going to itself be at most t. I guess, does anyone see why this might hold? It probably is, this is not a trick question. This should be relatively straightforward. This is just, I guess, in definitions. Okay. Yeah, okay, so I guess the idea is, if x and t come from the epigraph set, maybe it's good to, for me to go a little slower if people aren't following. But, I guess if x and t come from the epigraph set, then it must be the case that x was originally feasible in my constraint set, which is to say each of the qi's were individually non-positive. And furthermore, right, t had to be at least the value of q naught, right? So q naught here is at most the value of t, right? So when you aggregate these terms together, right, q naught is going to contribute at most t, and each of these quantities here are going to be non-positive, okay? All right, so pictorially that might look like this picture on the left, right? I'm going to, for each gamma, right, if you give me a gamma, I can consider the quadratic function q sub gamma, and if I consider the epigraph above q sub gamma, right, that is a set all x and t such that t is at least q sub gamma of x, right? That just corresponds to this expression on the right here. Then what Lagrange aggregation tells us is that the original epigraph, right, this blue set, is necessarily going to lie within the green epigraph, right, the one that I'm getting from aggregation. And this holds for any gamma, right? So, if I take another gamma prime, I'll get a different set, but this different, this other green epigraph is still going to contain my original blue non-convex epigraph. Okay, so, this is a tiny bit of an issue because I guess what I was really hoping for was I was trying to build valid inequalities for my pink convex hull, right? I wanted to be able to hopefully find this pink convex hull using quadratic functions of this form. But unfortunately, right, you can see in this middle picture here that this green epigraph is actually going to cut out a portion of my convex, the pink convex epigraph. Okay, so I guess what I'm going to do here is I'm going to try to fix this, and I'm going to fix this the simplest way I can think of. Okay, so what I'm going to do is I'm simply going to consider the gamma, right, these aggregation weights for which q sub gamma, the aggregated quadratic function, is convex. Okay, so I'm going to define this capital gamma set. It's going to consist of the non-negative aggregation weights such that q sub gamma is convex, and that's going to define some region in space like this on the right here, like this yellow set here. Okay, for those of you who might be familiar with some of this terminology, right? What I'm going to do is this capital gamma set is simply going to be the set of gamma such that the aggregated quadratic form, right? What would be a sub gamma is positive semi-definite. Okay, and now I guess what I said previously is that if you give me any gamma in gamma now, right? So this is not any arbitrary gamma, which is not negative anymore, right? I'm additionally assuming that q sub gamma is convex. Then now I have that for any x and t in the convex hull of the epigraph, so not just the epigraph anymore, I'm also going to have this inequality, right? It's necessarily going to hold that q sub gamma of x is at most t. So pictorially, right, what this means is that I've found some inequalities that I can impose that are going to be valid for this pink convex hull. Okay, so pictorially that might look something like this. Okay, so I guess this was a little bit technical, but why did I bring this up? So I wanted to tell you about this set of convex Lagrange multipliers because it actually captures very well, in a sense, what the SDP is doing. Okay, I claim that the SDP is going to simply look at this set capital gamma, and it's going to try to impose all of the constraints that it can, all the Q sub gamma constraints that it can find of this form. Okay, so more formally, we proved this lemma. Right? It says that under some technical conditions, the SDP epigraph, right, that was this green set on the left here, is going to be the set of all x and t such that Q sub gamma of x is at most t. And this has to hold for all gamma and gamma in capital Gamma. Okay, so I'm going to try to illustrate this for you now down here. And I've just drawn for now the special case where capital Gamma is polyhedral. Okay, where capital Gamma, you know, is a convex hull of these 4 vertices. Okay, and now I'm going to recall that, you know, for any fixed x, Q sub gamma is actually linear. And so this maximization is going to be achieved at one of the 4 vertices. Okay, so that is to say, you know, I can think that each vertex has some idea, you know, each vertex corresponds to some gamma, and you know, I can take the Q sub gamma epigraph at each vertex. You know, each vertex will give me a different one. But what this lemma is saying is that if I simply take the intersection of all 4 of these epigraph sets, then I'm necessarily going to get the SDP epigraph, right? It's going to be exact. Like, this is exactly what the SDP does. Cool. So, you know, this, I guess in this illustration, I have assumed that gamma is polyhedral. Okay, so in general, this is not going to be true. Why? Maybe I'll just draw some more pictures. Right, so gamma, recall, is the set of, you know, it's a set of Lagrange multipliers for which Q sub gamma is convex. That is to say that this quadratic form, this aggregated quadratic form, is positive semi-definite. Okay, and the set of gamma, the set of, I guess, lowercase gamma that satisfy this, you can think of as the following picture. Right, so here is this picture. On the left, I'm thinking of working over the symmetric matrix space, right? I'm working over the space where the A sub I matrices live. Okay, and within this space, there is some cone that corresponds to the positive semi-definite matrices, right? That is this cone here. And what this inequality is saying is, you know, I can imagine that I'm going to start at A0, and I'm going to consider the orthant coming out of A0 in the A1, A2 through AM directions. Okay, and I'm going to look at which lowercase gammas satisfy that this orthant is going to stay inside the positive semi-definite cone, or where it's going to intersect the set of positive semi-definite matrices. Okay, so in this example, that would give me the semicircle here, or this, I guess, quarter circle, which is clearly not polyhedral. Okay. But there are, you know, indeed there are cases where you are going to get polyhedral gamma, like in this picture here. And I claim maybe the first example that you might think of is the case where the AIs are diagonal. Okay, so this holds because, you know, if the AIs are diagonal, then in this case, I claim, you know, this this funny inequality sign is going to correspond to simply just saying that these A sub I matrices are actually just non-negative, right? Each of the diagonal entries is non-negative. Okay, and so that will actually give you a polyhedral region. Cool. Right, I guess towards the beginning of this talk, I was saying that I would make some assumptions on the geometry of gamma, and that's what I would think of when that's what I mean when I think of saying that the A sub I matrices, the quadratic forms, are interacting nicely. Okay, so what is this assumption that I'm going to make? Well, I'm just going to assume that gamma is polyhedral for one of the results I'm going to tell you about today. Okay, and in my mind, gamma being polyhedral is capturing the fact that these quadratic functions, these quadratic forms, are interacting, you know, about as nice as they can interact. It's almost as if these quadratic forms are diagonal, are each individually diagonal. Okay, I guess, you know, the reverse implication is not true though. So it's actually capturing a larger class of problems, not just the diagonal problems. But, you know, for now, maybe as a first pass, you can think of this assumption that gamma is going to be polyhedral, that's going to play a role later on as maybe just saying that the A sub i's are diagonal. Okay, so now I'm going to move on and tell you about symmetries in the quadratic forms. We defined this notion of symmetry, which we call the quadratic eigenvalue multiplicity. It's going to be the largest integer k between 1 and n, such that each of your A sub I matrices can be written as a block diagonal matrix, right? I'm going to ask that it can be written as a hat A sub I Kronecker product with the I sub k, or the k by k identity matrix. And pictorially, what this really means is that just that each A sub I is actually some smaller hat A sub I matrix repeated k times down the diagonal. Okay, maybe I'll do some examples. All right, so this is an example where n is equal to 4. Okay, this is an example where the x variable, this variable that we're optimizing over, lives in R4. Okay, so I guess if you see this quadratic form, if you see this term in your quadratic function, maybe with some other, maybe with a linear term and maybe with a constant, but if you see this quadratic form, you can ask what is the matrix, right? The A sub I matrix that induces this quadratic form, and in this case, that would be this this identity matrix. Okay, and you can think of the identity matrix as being a 1-by-1 block of a single 1 repeated 4 times down the diagonal. Okay, each of these is its individual block. And in this case, right, we would have that k, the quadratic eigenvalue multiplicity, is equal to 4, right? That corresponds to the block multiplicity. As another example, you might encounter this quadratic form in one of your constraints. If you write out the matrix that corresponds to this quadratic form, you would get this in the middle here. And you can think of this matrix as a 2-by-2 block, right? This 1, -1, -1, 1 block, in this upper left, repeated twice down the diagonal. And in this case, we would have k to be equal to 2. Okay, so now I can finally get to some of our results. Okay, so in this first result, and I guess I should say that I'm going to call all of these results corollaries today because I'm not writing them in their full generality. But it's close. So in this first corollary, it says that if gamma, right, the set of convex Lagrange multipliers that is somehow capturing how these quadratic forms are interacting with each other, if this set is polyhedral, and k, the quadratic eigenvalue multiplicity, right, how symmetric my instance is at least the minimum of these two quantities, then I will have the convex Hull exactness. Okay. So maybe this expression here might be a little hard to parse. So maybe I will I'll go through it slowly and I'll run it through some examples for you. Okay. So first, what is this expression saying? It's saying that k needs to be at least the minimum of m. Recall that m is the number of constraints in your problem, and the number of linear forms, the number of non-zero linear forms in your constraint set plus 1. Okay. So as a first example, I'm going to claim that the assumptions of this corollary hold whenever m, the number of constraints, is equal to 1. Okay, so why is this? Well, gamma, right? Why is gamma going to be polyhedral? Well, gamma is going to be some convex subset of r to the m, in which case, in this case, r1. And so it's necessarily going to be an interval and thus polyhedral. Furthermore, k, recall, is always going to be at least 1, right? We can always write each A sub I matrix as itself Kronecker product with the 1-by-1 identity matrix. Okay, so I claim k is always at least 1. So this second assumption is going to hold, and we can apply our corollary in the case where m is equal to 1. Okay, so this actually recovers a well-known and famous result known as the S lemma. This is a result due to Yakubovich from 1979. I guess when it was first proved, I guess people only cared about the second inequality or the second identity, but this first identity, at least was not recorded until a few years ago. Cool. Another example where this holds is where the a sub i's are each diagonal, right? So gamma, recall, is going to be polyhedral in this case. And when the b1 through bm are each equal to 0. Okay, that is to say, when all of the linear forms in the constraints are equal to 0. Or in other words, when the constraint set is centered around the origin. Okay, and this is going to hold simply because the second term in the minimization is going to be equal to 1, and as I've already said, k is always at least 1. Okay, and this is actually the I guess this is the version of the corollary I used to generate all of the pictures today. Cool. And finally, another example where this holds is the case where the a sub I matrices are each scalar multiples of the identity, right? In this case, we'll have k to be equal to n. And if n, the dimension that you're working in, is at least m, the number of constraints. Okay, so I will illustrate this this third, I guess, example for you on the next slide. I think there's some fun pictures to see for this example. But before I move on, I do want to say that we are not the first to study this problem. There are a lot of other results that are similar or related, and in particular, you can find pointers in the full version of this paper or in this paper by Buer and Ye from last year. I guess I do want to highlight that the main contribution of this work is that we capture quite a few of the sufficient conditions that are currently existing in the literature under a single framework, right? A single analysis. And in many cases, we can actually extend some of the known results. Okay, so I think the nice part, the contribution of this work is just its explanatory power. Cool. All right, so now let me, I guess, draw some pictures for this last example here, this third case. And this example is what I call the Swiss cheese example. Okay, so you can imagine maybe you're an ant, lying at the origin in high dimensional space, and maybe there's this piece of Swiss cheese that's out there in high dimensional space, and you want to find the minimum distance that you need to travel to get to this piece of Swiss cheese. All right, so I'm going to minimize this, the squared distance to this piece of Swiss cheese, right? I'm going to find x in this piece of Swiss cheese here. And I guess what I'm going to assume is I'm going to assume that this piece of Swiss cheese, this non-convex object, is defined by 3 types of constraints. Okay, the first constraint is going to say, that your ball, that your Swiss cheese must lie in the intersection of some number of spheres, right? They can be of arbitrary radius located in arbitrary centers. Your second type of constraint is going to be able to say that your Swiss cheese must exclude a union of some number of spheres. And finally, you get to also impose linear constraints. Okay, so then I guess what to note here is that each of these 3 types of constraints can actually be imposed using quadratic constraints. Okay, in the first case, that would correspond to the case where the quadratic form is the identity matrix. The second case corresponds to the case where the quadratic form is the negative identity matrix. And the third type of constraint is just where there is no quadratic form. Okay, so it's equal to 0. Okay, so again, in this case, we can apply our corollary from the previous slide, right? I guess really the corollary of the corollary, right, because each of these matrices is a scalar multiple of the identity matrix. Okay, so then the result from the previous slide would say that as long as your piece of Swiss cheese is non-empty, and n, the dimension that you're working in, is at least m, the number of constraints, then the standard SDP relaxation is actually going to solve this problem for you exactly. Cool. Okay, so I'll move on now, and I'll tell you about one more corollary where we can get rid of the polyhedrality assumption. We're going to get rid of the assumption that gamma is polyhedral. And I do want to mention this quickly just because this is the version, this is the result that we will be using for the robust least squares example. Okay, so in this result, we managed to get rid of the assumption that gamma is polyhedral. I recall that this was the assumption that somehow was requiring that our quadratic forms interact nicely with respect to each other. Okay, This corollary says that even if you don't have polyhedrality, as long as your K parameter, right, the symmetry parameter is large enough, we can still recover both the convex hull exactness and objective value exactness, right? We will need K, this symmetry parameter, to be at least m plus 2 or m plus 1 respectively. Okay, and this result here is highly related to a line of work that was started by Beck in 2007 on quadratic matrix programming. I guess the exact details of the connection are a little difficult to spell out, but I'm happy to chat about this after the talk. If you want, you're welcome to ask this as a question after the talk. Cool. All right, so I'm going to use this corollary, and I'm going to give you an example application to robust least squares now. Right, so first, the problem of least squares. Right, we're given some number of data points. These are the y star i's, right, these green points here. And I'm going to collect it into this matrix capital Y star. We're also given Z1 through Zn. These are maybe the results of some, measurement on this Y star, on these Y star i's, right? So this corresponds to the heights, these blue heights in this picture here. And in the least squares problem, we're asked to find a linear estimator, right? Some L that minimizes the distance between Y star L and Z. Okay, this is the least squares error. Okay, so what is robust least squares and how does it differ from this? Well, I guess the main idea in robust least squares is that, in reality, we seldom have exact access to the Y star i's, right? We don't actually know what they are exactly. Maybe all we have is some Y hat, right? This is an estimate of what Y star should be, but we're guaranteed that maybe Y star lives within some small region around Y hat. Okay, so pictorially, that's these green sets here. Okay, and now, we would still like to be able to minimize the least squared error with respect to the true Y star, but because we don't know what Y star is, we're just going to have to minimize the worst case error, okay, over all possible x's in this uncertainty set. Okay, so this is the minimum of the worst case least squared error. Okay, and what's cool here is that as long as this uncertainty set is defined by quadratics, we can actually apply our theory. Okay, and in particular, in order to apply our theory, you do not need to assume that these quadratics are convex. Right? You can have non-convex uncertainty regions. Okay, this might come up, for example, if you have information that tells you that for whatever, maybe physical laws or whatever, that Y star cannot lie in some regions. Okay, so we're going to mostly focus on this second part here, right? This maximum term. And I guess for this example, I'm just going to assume that this uncertainty set is defined this way. Right, that is defined as the intersection of some number of norm balls. Right, that's what this constraint corresponds to. Okay, so then I'm just going to rewrite what the maximization problem, the inner maximization problem on the previous slide was. Right, we're maximizing over x such that x belongs to this uncertainty set, which I'm assuming is defined according to this first equation of this least squared error. All right, then what I'm going to do is I claim I can actually rewrite this as a QCQP, as a quadratically constrained quadratic program, in the variable x. Right, this lowercase x is actually, what I'm going to do is I'm going to imagine that I have this capital X, and I'm going to stack each of its k many n-dimensional vectors on top of each other, right, to get some vector of dimension r to the nk. Okay, and what I claim is that when you do this, you're going to note that all of the quadratic forms in your problem now look like L sub I transpose L sub I, Kronecker product with the k by k identity matrix. Okay, and so in some sense, we're going to have a high symmetry, where you're getting exactly the symmetry parameter k is going to be exactly the dimension of your problem. Cool. So if we apply the results from the previous corollary, this is going to say that as long as k, right, the dimension that your data points live in, is at least m+2 or m+1 respectively, we're going to get the convex Hall exactness and objective value exactness, right? And this, continues to hold even when your uncertainty regions are not convex. All right, cool. So I'm going to begin to wrap up now. Right, in this talk, I told you that QCQPs, it's this cool family of optimization problems that we might care about, but in general, they are NP hard. What we decided to do instead was we simply said, okay, let's just solve the SDP relaxation and try to understand when is it true that the SDP relaxation is exact. Okay, and we did this by analyzing these two objects. Right, the first object is the set of convex Lagrange multipliers, and in particular, we made some assumptions on its geometry. The second thing we analyzed was this symmetry parameter k, which we were calling the quadratic eigenvalue multiplicity. And I told you about some results in this direction, right? I showed you that, or I claimed to you at least, that as long as k is at least the minimum of these two quantities, right, the number of constraints or the number of non-zero linear forms plus 1, then you get the convex Hall exactness and objective value exactness. But crucially, this was in the case where gamma was polyhedral. I also showed you that if k was slightly larger, right, if k was at least m+2 or m+1 respectively, we could recover these two results in the case of general gamma. Okay, so what are maybe I'll tell you about some current and future work. So the first thing is that when you look at this table, there does seem to be a bit of a gap between these two quantities, and for a while it took us a while to try to understand what is there a fundamental difference between the case of polyhedral gamma and general gamma, and if so, why qualitatively is there a difference, and can you knock this parameter down a little bit to something that looks more akin to this thing in the first column. And we have some results in this direction, and hopefully maybe I'll be able to tell you about this in a future theory lunch. A second question in this direction is, are there conditions that we can get that only depend on the constraint set, right? That do not depend on the objective function, right? Maybe to motivate this question, you can make this analogy between integer programs and linear programs with quadratic programs and SDPs, right? In both cases, you have one thing which is hard to compute, and you have another which is easy to compute. And in the integer linear programming case, right, we have these conditions that ensure that our domains, our feasible domains, these polyhedra are integral, right? That is to say, if you optimize any objective function over these sets, you're necessarily going to get some integer solution. Okay, and so this question here, you can think of it as being a direct analogy of this property, where we're asking that if you can optimize any quadratic objective function and still get exactness. Okay, and along with my collaborators CJ Argue in our math department and Fatma Shazan in Tepper, we have some results along these directions. There are some additional number of open questions in this area as well. And finally, this is, I guess, true future work. So a lot of this framework that we've built so far and what we've used it for is to analyze exactness results. But in general, we're not going to expect exactness to hold too often. So an interesting question is whether or not there are approximation results that we can derive for problems that have maybe geometry that is nice but maybe not so nice as having polyhedral gamma, or maybe what happens when k is close to being these values here but not quite. Okay, so so these are some interesting questions that I'm interested in working on and plan on working on in the near future. Cool, so I'm going to wrap up here, and I'll say that you can find these slides on my website, You can also find the full version of this paper on arXiv. But yeah, I'll stop here and I'll take questions now.
I'll just jump in then if I can ask a question.
Sure.
Yeah, thanks for the talk, Alex.
Yeah.
I was wondering, is there an obvious reason that gamma should be non-empty, or could it be the case that you have some annoying QCQP where it is empty?
Yeah. So gamma can be non-empty, right? So this was part of the, if I jump back here. So, in all of these corollaries, right, I'm assuming dual strict feasibility. So this is a slightly annoying technical condition that I didn't talk about too much. But this dual strict feasibility is going to ensure that, what does it correspond to? It literally means that gamma is assumed to be strictly non-empty, right? There's actually going to be some aggregation for which you can get a positive definite A sub gamma. Okay, and I guess why is this necessary? Or why would you make this assumption? I guess the idea is that if you don't make this assumption, then the SDP is necessarily going to take a value of negative infinity. Okay, and so if you don't make this assumption, it'd be hard to get results of this type unless you can also somehow magically have that the QCQP is taking the value negative infinity. Yeah, so I guess I'm not quite aware how to deal with this problem if you don't have dual strict feasibility. We do have a way of dealing with it in the case for m equals 1 when there's a single constraint. But in general, it's not clear. It's not clear whether you can recover results like this. Maybe I should say that in the case of m equals 1, how you deal with this is you just do some perturbation argument. But in the case of larger m, it's unclear to me. Maybe I'll think about this some more and maybe get back to you. But at least it's not immediately clear to me what to do.
Okay, great, thanks a lot. Yeah.
I had a question. So QCQPs are NP hard in general. So presumably you can't get these tight exact relaxations for general QCQPs. I was wondering sort of how far from tight are your K bounds? Like if you take one of those NP hard instances, how close can they be to the bounds that you have that will guarantee tightness, exactness?
So I guess, are you thinking of maybe taking some NP hard instance and just trying to figure out what the value of K is for those instances? Yeah,
are there NP hard instances where K is m minus 1 or something like that?
I see what you're saying. I see what you're saying. You're asking, sorry, let me go back to this conclusion slide.
Yeah.
So you're saying if, maybe you're going to consider the problem where, these bounds are actually let's say m over 2 or something.
Oh, yeah.
Then is it still true that this class of QCQPs is NP hard?
Yeah, that's right.
Yeah, that's a good question. That's actually not a question that I've thought about, but it is interesting. Maybe I can give you an answer to a question you didn't ask, but maybe it's slightly along these lines. These K bounds are almost tight in the following sense, right? So, so this on the left here, right? We know that okay. So I guess what I've written on this slide is the quantity that I said that I stated in the corollary, but the actual version in the full theorem is tight in the sense that there do exist instances where you have this quantity minus 1 for which objective value exactness does not hold. And furthermore, even with the same amount of symmetry, if you switch from polyhedral gamma to general gamma, you can also break the same result. So I guess I guess what I'm saying is that at least for this result here, you can't get rid of this minus 1, and you also can't get rid of this polyhedral assumption. Whether or not those instances are still NP hard, yeah, that's a cool question that I haven't thought about, but maybe I'll think about this a little offline.
All right, thanks.
Alex, I have a question. Can you hear me?
Yep.
Have you thought much about the approximation results direction? Because, like, I guess I'm wondering what a natural notion of approximation is. So multiplicative guarantees seem out of the question because you can just shift things to the optimum is at 0.
Yeah, so I guess in this world, a lot of the approximation results, what they look like is, you know, you look at, if you give me your QCQP, you know, first, I guess the first thing is that they always assume that the domain is bounded so that there exists a minimum and a maximum value that the objective function can take. And then the multiplicative guarantee is just, you know, as a factor of this, how do I put this? As a factor of this maximum gap that you could have, how far off are you? So that's, you know, the general form that these approximation results would take. I have thought about this problem a little bit, but maybe not in the usual sense of the word approximation. So what I have thought about is, you know, you can think, right, instead of exactness, maybe I'm just going to assume that I'm going to ask for, like, when is it true that, you know, it's maybe within some, maybe some error of the true value. And, you know, results of this type, or conditions that would ensure results of this type should be, you know, in some sense, stable to a little bit of perturbation, right? If you have an instance which has a good SDP relaxation and you perturb it a little bit, you know, you would hope that that the SDP relaxation would still be good. Okay, and along these lines, a question that I think might be interesting, or a question that I thought about a little bit, is if you have maybe, right, I guess, you know, both of these conditions, right, the fact that the convex Lagrange multipliers are polyhedral, or the fact that you have some amount of symmetry at all, each of these are very, very brittle to perturbation. As soon as you, like, change your data a little bit, the instance data, both of these things can break, you know, completely. And so a question is, like, you know, if you gave me an instance that was close to, you know, it was nice in some sense, maybe it's like close to being polyhedral, or maybe it has, you know, some structure that indicates maybe it's close to another instance that has large amount of symmetry, can you find those other instances? Right? I guess this is more of like a trying to find nice instances that are close by question.
I see. So, but by nice, you would still mean like the relaxation.
Yeah,
or something. Yeah.
Yeah, exactly.
I see.
Yeah, yeah. Okay. I guess, you know, yeah.
Okay. Thanks.
Yep.